Oh, good day, everybody. Welcome to week 3. This week we're going to be talking about heat. And when we're talking about heat, we're not just talking about hot air flow and how that moves or temperature. At this point, we're going to be talking about the transfer of heat energy. So first, before we get into that, a person who you might recognize on the next slide has played an important role in this, as he has in a number of other things. My guess is you will recognize him. Right. So we have Albert Einstein. We'll be talking a little bit about the transfer of energy and especially how that relates to heat, and especially his famous formula, E equals mc squared. Now, don't get too worried about this. We're just going to apply this in a very general sense. We're not going to be going down the rabbit hole and trying to figure out the entire theory and go into a very deep explanation. It's going to be more of a general overview of how the vibration works on a very small level of particles and what impact that has, and in terms of how it transfers heat. So uh, don't get too worried about it. Okay, let's get going. So as you take a look at the slide, it's basically talking about how everything is made out of electrons, protons, and neutrons, which is the smallest level that we're considering. And then you look at that as, and then above that is atoms, and then atoms make up molecules. Okay, so that's basically the hierarchy of how all this works. When we talk about this, they all vibrate all the time if they're above absolute zero. And this is where we got that 273 degrees Celsius to Kelvin conversion, right? So in order to go from Celsius to Kelvin, you add 273 degrees because 0 Kelvin is minus 273 degrees Celsius, right? So that's how we got last week when we were doing that exercise. That's how we got this number. And that all has to do with the vibration of all these molecules and electrons and atoms and protons and all this fun stuff. So one thing to look at here, we're considering hydrogen atoms versus the molecule. So when you're taking a look at a single atom, right, that's atomic hydrogen. And if you're looking at H2, which is two atomic hydrogens, right? So when they combine, you have a hydrogen molecule, and when they're single, you have atomic hydrogen. Heat energy is the energy of vibrating molecules in a substance. One thing to note is when we talk about temperature, temperature is the average vibrating heat of each of the molecules in a substance. So that means that the temperature is the measure of the concentration of heat within a substance. And I'll explain that a little bit more in the upcoming slides. The best way to do that is with an example. In this example, we have two beakers of water, and they start at the same temperature. Now, one has 1 kilogram of water and is heated to 2 degrees Celsius, which means 2,000 calories are added. For our purposes, a calorie is the amount of heat required at a pressure of 1 atmosphere to raise the temperature of 1 gram of water by 1 degree Celsius. Okay, so here's a definition at the bottom. And when we talk about calories, I'm not talking about the burrito that you had for lunch, but even in that case, calories are not that far off in terms of a measurement of energy, right? So the other beaker contains 3 kilograms of water, but is only heated to 1 degree Celsius, right? So this one is heated 2 degrees Celsius, this one is heated 1 degree Celsius, but it contains more water, right? So the second container contains more heat, but the first one has a higher temperature because the heat energy is concentrated in a smaller amount of water. So let's take a visual look at this. Here are your two beakers. This one has a smaller amount of water, but is heated up to 2 degrees, which is a higher amount of heat. So the temperature will read as higher And over here we have a larger amount of water, but it's only gone up by 1 degree. Right. So over here, there's less concentration of heat because you have a larger amount of water, right? But over here, there's a larger concentration of heat because you have less amount of water. Now, this is also an important aspect. So, like, when we're talking about the oceans getting warmer from an environmental perspective, this is because there's such a large amount of water, and even if it's getting heated just by a little bit, it can have such a profound impact on our climate. So that's one way to also consider how this applies to us in the real world. So when we're taking a look at an example like this, if the outside air is minus 18 and the inside air is plus 22, right? In this direction, which way is the heat moving, right? And one thing to consider is that heat will always go from high concentration to low concentration. And it'll always go from heat will go to where there is no heat or less heat, but hot air will rise, and that's something to consider. That's different. So when we're talking about hot air rising versus heat, that's a difference. So it's always going to go from one temperature to another at a lower temperature. So the outside is 18 degrees and the inside is 22, right? So this is the brick on the outside of the building, and this is the insulation on the inside, and here's your drywall. You're going from the inside to the outside. So heat is going to go from where there's heat to where there is less heat or no heat. If we're saying no heat, then this is minus 273 degrees Celsius at that point. Right? So heat always flows from hot to cold, right? And this is to keep in mind. So when we're talking about hot air will rise, but that has to do with the air molecules as well and how they react with everything. But to consider that heat will go from always hot to cold. And it only goes in that direction till a balance is achieved. So both places, if the inside and outside are 22 degrees, then you're not going to have any heat flow, right? So in that diagram, when we're looking at the outside to inside from minus 18 to plus 22, if now suddenly it's summertime, inside and outside is 22, there is no heat flow. On a building, you can see exactly how this works. Especially in the winter, you have heat that's going from the inside to the outside and vice versa in the summer. And obviously, this will keep happening till a balance is achieved, which is rare in the winter time. So you generally have heat that's always going into one direction. So the reason why we have insulation is because insulation slows down that process, right? So if you have no insulation, you lose it really fast. You lose heat really fast. So heat goes to where there's no heat. And the idea is what you want to do is be able to capture the heat from the furnace, the people, the sun, and other things, and that's going to the outside. So if you want to maintain a steady temperature inside, the amount of heat added must equal the amount of heat lost. And that's what you're trying to do, is create that balance. So when you're actually when heat is moving, so the colder it is outside and the less insulation that you have, so the faster heat is going to leave, so the more your furnace has to work, or I guess the more people you have, or the more sun you need coming in to heat up your space. So all of those things can have an impact. An easy way to do it is to actually just take a look and compare the two, and compare like an efficient house to a house that's not so efficient. So over here, we're going to compare two houses. One that's a more conventional home, and then you have an energy efficient home. So here we're also looking at things like passive houses or near passive houses, or pretty good home, and there's a bunch of different categories. Some of materials like this are also in our folder that you can take a look at as optional reading that will give you more of an idea of how it's done. And so certain things, if you were to keep a conventional home and an energy efficient home, will be the same. Let's say the amount of heat generated by your stove, the heat generated by your light bulbs, for example, but also your refrigerator, anything that takes electricity, anything that has motors that's generating heat, all of those remain the same. Now, a conventional home gets some of its energy from sunshine because it has windows, but it's not optimized if you're to look here. So if you look here, the amount of energy you get in an energy efficient home compared to a conventional home is the same for your cooking and your electricity. So let's assume that those are the same, and you can make those a little bit more efficient in an energy efficient home, but for our purposes, let's keep them the same because you can't really get that much more efficiency out of it. But where an energy efficient home will take extra advantage of the sun, like having more windows on the south side or fewer windows on the north side, so you have less energy loss and more sunshine coming in, especially in the winter, having the right kind of overhangs. And we'll get into these details a little bit more later on in the course, but just to give you a general idea, a part of the amount of energy heat gain over here is going to be in the house from the sun, and you can see that that's pretty significant. And over here, let's assume it's the same number of people in both homes, and we all, like I said, are heat generators and vapor generators. We generate moisture and heat, and so those will be the same for both the homes. And the biggest difference is how much heat comes from a heating system. And so for a heating system in a conventional home, you now have a significant amount of heat that is required to be generated to make up for the heat loss. So up here you have the heat loss that goes from this bar all the way to this bar. And so the minute you start to reduce your heat loss by better insulation, better air sealing, better home design to take advantage of the sun, you now require a very little heating system, if any. So if you actually look at some passive home designs, they actually don't have any active heating system. They're all passive by design, and that's how it gets its name of being a passive home. So take a look at some of the information if you're interested more in this. In terms of a passive home in the folder, there's a couple of good articles about energy efficient homes in the folder for this week. And over here you can see, like, now if the cost of heating or let's say natural gas goes up, or cost of electricity goes up, if you have baseboard heaters, you can see that the cost makes a huge difference in a conventional home. But over here, even if the cost were to double of whatever system you're using, you would now be out to here, right, in terms of how much it would actually cost you. But then if the cost of all this heating would double, that would be a lot more in terms of your yearly costs. So a lot of times when you do home comparisons, you compare energy bills and see what the energy bills are, and then you can also rate them for the future. And so a lot of times the insulation will pay for itself, and that's excluding the advantage of insulation of making the house more comfortable, quieter, cleaner, all those things. Now, I want you to pause the video here for a second, press the space bar, pause it, and take a look at this image. I'll briefly describe it to you and then say pause so you can see what's going to happen. What I want you to see, so this is using an infrared camera and showing the heat loss. Basically, the more heat loss, like the brighter the color. So you have very little heat loss, say in this space up here, and you start to have a little bit more heat loss and the greatest amount of heat loss over here. So I'm going to ask you to pause the video, take a look at this picture, and then unpause it and come back. So pause. Okay. So now that you've taken a look at this picture, let's take a look at a couple of things. You can see that there's certain areas of the home that have a lot more heat loss, and generally you can see that around which areas. Pause. It's the windows, right? The windows and doors have the most amount of heat loss because they have the least amount of insulation. So heat is able to move very easily through those areas. One interesting thing I noted a number of years ago, if you look at the cars, can you tell anything about the 4 cars that are here? Pause. You'll notice that the 3 cars over here are quite black or blue, so there's not a lot of heat being generated over here. But you can tell, you can by how white this is and orange it is and red it is, that this car was recently parked. So the engine is still warm, but the rest of the car is cooled down, because that's going to be the last part that's going to cool down in the car. Okay, so I have one more thing to notice over here. So just take a look at this building over here. And what could be the possible reasons that there you have heat loss in this window, heat loss in this window, heat loss in this window? Oh, but take a look at this window. There's very little to no heat loss in this window. So just pause the video for a second and have a think. Pause. So the possible reasons can be that A, this is a separate room and the windows are open and the whole room is super cold. But a more likely scenario is that they have a curtain, a thick curtain that's been drawn, so that's helping keeping the window surface cold, so closer to the outside temperature, while keeping the heat inside. Okay, so that's another thing you can look at because of an infrared photo or a thermogram. So here's another picture that I want to share. So this is actually a passive house. So there's more passive house information over here. If you take a look at this link, and then this picture is from this article. So take a look at these buildings. These are some row homes, and obviously it's pretty obvious there's one building that looks different than the other ones. That's this one over here. So there's two possibilities of what's happening with this building. So pause for a second, think about it, and then come back. So pause. So if you take a look at this building, you see that there's not a lot of heat loss. The one possibility is that there is, there's like it's in the middle of winter and all these houses have heating and they have all the heat loss, but this one doesn't have a lot of heat loss because it's actually not warm. The house is very cold. And that's possibly correct, but probably not, because just around the entrance door and just around some of the windows, you can see some heat that is managing to escape. And you'll notice that heat is also escaping at the highest points and less at the lower points, right? And this has to do with how hot air rises, which means you have that stack effect. So the area up here is technically a little bit hotter. And and because it wants to equalize, just like pressure, that heat wants to go to where there's no heat, so it's trying to escape. So try to escape more at the top than at the bottom. Okay. Doors being the exception, because you tend to not have a great seal around the doors, so heat will go to where there's no heat in any way place that it can. So that's what's happening here. So this is a passive home, and this is a very well insulated home, so very little heat is escaping, which means in the dead of winter that this house is super comfortable, not only requiring very little heat to be added in because of the amount of insulation that it has, and because of this and how airtight it is, and well ventilated it is because of the systems that they use, but it's also super comfortable. And people are like, oh, well, passive homes are really expensive. I can't do that to this home, for example. You must need a lot of money. But if you're building new, there's been certain cases where the costs of building a passive home to a conventional home, basically by changing some of your finishes, for example, you could actually have them at pretty much the same cost. But if you're to maintain the same finishes, you can actually now build passive homes with a simple design between 5 to 10% more of an entire building, which might seem like a lot, but I want to give you another perspective on this and something to think about. And what I'm trying to bring also into the course is this concept of resilience. A lot of you might remember the ice storm, for example. So when you think about the ice storm and people lost power, I had one student in a previous class, when they lost power, they had lost power for 11 days, and that was really, really uncomfortable in the middle of winter. Imagine you have a relative or somebody who's in a wheelchair who can't leave the house that easily. And so now suddenly it's not only a matter of being comfortable, but it could also be quite dangerous, especially if you have an ice storm and there's not a lot of facilities available. And then you have a house like this that's super insulated that even with no power is super comfortable. And the cool thing about a passive house is because it requires so little heat, one way to generate heat is to actually invite your neighbors over whose houses are super cold. And guess what? Like I've said before, people are heat generators. So just the heat from the humans in this house would make this house more comfortable. Whereas over here, it's not going to make much of a difference because all that heat is being lost through this brick coming out, and the house still feels cold. You can see how cold it is in some of these windows. And so over there, it's a great example of whether it's super hot or super cold and electricity is gone, that your house is not only comfortable, but is also a safe place to be. Okay, so what I want to talk about now is to talk about how heat moves. And heat moves in three ways: conduction, convection, and radiation. And the easiest way to understand these three quickly is to take a look at this next slide. So you light a match, right? You have convection because you have hot air that moves up, and that's the convective forces. The heat that you feel coming off of the flame back towards your fingers is that radiant heat, right? That's a radiation. And as that moves around, so conduction would mean if this, say, was made out of metal, you might feel a little bit coming from the wood. It's not as strong, but you still have heat moving by conduction. Like, for example, the wood right over here would be super warm, and so if your fingers are here, you would also feel the radiant heat a lot, and you would also get some conduction by through the wood. But if it was metal, for example, you might feel it a lot more. But this simple picture can illustrate all three: conduction, convection, and radiation. But let's understand all these three concepts a little bit more in detail. So conduction, we think of this as heat transfer through solids, but it's because of a temperature difference, and that's how it moves through the solid, through any substance. So basically, the easiest way to think about this is it's a transfer of vibrating energy between molecules that are next to each other, that are adjacent to each other. So when you touch a cold surface, your hand feels cold because the heat energy is going from your hand to the cold surface, right? It's not the cold is coming to you, it's that your hot hand is losing heat to the cold, right? So cold is just the absence of heat. As a condition, it doesn't exist theoretically. You're losing more heat, and that's what makes you feel cold. So let's take a look and see what this looks like. So in this diagram over here, I'm applying heat to the molecules over here, and these will vibrate the most, and they're giving off the most amount of heat. And so as it gives off heat and as vibration, it's now vibrating this molecule here, which will take some of that heat, and then that will vibrate and lose some of that energy as heat to this molecule over here. The example that I like to illustrate this is with a cast iron pan. So a cast iron pan, a traditional cast iron pan, is made out of one piece of solid cast iron metal. And if you leave it on the stove for too long and you walk away from it and you come back and you touch the handle, what does the handle feel like? The handle feels really hot. And because that handle feels really hot, you feel the heat transfer that comes from the base of the pan all the way up. Now, if you had held that handle of the pan, you could feel it slowly warming up, because as the base of the pan, you have a lot more vibration going on and transferring that heat. And as that heat, as this continues to vibrate, it sends more vibrations this way, which then this starts to vibrate more, which then starts to vibrate this more. And so that heat keeps getting transferred all the way to the handle, and that's why it feels so hot. So this is basically that explanation. The molecules closest to the heat source begin to accelerate and collide with more force. You have kinetic energy, which is the energy of movement, and that's exchanged with each collision, and heat energy is transferred by this mechanism in conduction. So till the heat is evenly distributed, so basically everything is at the same temperature, basically all the vibrations are the same, you're going to keep getting transfer of kinetic energy. The main thing to figure out is what speed the heat will move at. So there's two things. So one is the type and thickness of the material. If we were to go back to that cast iron pan, the thicker the cast iron pan, the slower it is to heat up, and the slower it will also be for the handle to heat up. So even if you were to keep your hand, if you had two cast iron pans, one thinner and one thicker, and both stoves were at the same temperature, the one with the thicker handle would end up heating up much faster than the one that was thinner. The other one is the temperature difference between the hot and cold sides. If anyone has ever gone winter camping and you have a pan, you'll see like how much longer it takes for it to heat up compared to the summertime, and also how quickly it cools down, right? So that's the heat with which the speed at which heat is moving. So that's a good way to think about it, is if you have a cast iron pan in the summertime or cast iron pan in the wintertime, there's a lot more chance for that heat to escape because there's a lot more areas that don't have heat, and so that are able to take that heat and trying to achieve that balanced temperature, right? So to understand this about how much the total heat transferred by conduction is dependent on the exposed area being measured and the total time under cold conditions, let's go back out camping. Let's take a look at the pan. If you have two pans and one's a smaller pan and one's a significantly wider pan, and they're both the same thickness and both have, let's say, the same number of grams of water, the larger pan is going to get colder faster. And also, if you were to leave either one of those pans out for longer, that one is going to get colder faster compared to the one if you're magically have a hot tent or you're going back to a cabin, for example, which would be very nice. So generally, and for the purposes of our course, conduction, the movement of heat, is generally faster through solids and liquids, and faster through liquids than gas. So you have the molecules in a solid are a lot closer, and so that transfers energy a lot more efficiently. And when you have air or any most other gases, you have the molecules that are much further apart, and so the conduction is a lot less efficient. Materials that heat up quickly, we refer to them as conductors, and materials that transfer heat slowly, we think of them as insulators. Right now, when we take a look at this example, you can take a look at metals, for example, they're really good conductors, while wood and plastic foams and fiberglass can be insulators. But if you're then comparing wood to insulation, then wood would be a conductor compared to insulation like fiberglass, or even cellulose would be a better insulator because it's got a lot more air pockets and it's harder to conduct. And we'll get into that a little bit more. So sometimes some things that are conductors and insulators is a relative term because it depends on the two materials or three materials that you're comparing. So let's take a look. Let's see how this works. Okay, so in this example, we have three materials of the same thickness and the same temperature from the hot side and cold side, right? So over here, the input is the same. It's the same temperature on the hot side for all three. The three materials we're looking at here are concrete, and this is a particular density of concrete, which is 1760 kilograms per cubic meter. We have wood of the same thickness as a concrete with the same hot side, and we have a fiberglass bat of insulation. Normally you can think of this as the pink insulation that you might see at the big box stores or in a building, and the same heat being applied to one side. And this is also the same thickness as a wood, which is the same thickness as a concrete. Now, as you guessed, there's a lot more heat transfer on the concrete compared to the wood, but there's a lot more heat transfer of the wood compared to the fiberglass. And the biggest difference is between these two. So we have two things. One is the RSI value, which sometimes is also called the R value. It depends on the system, and I'll explain that a little bit more. But the difference between the systems, basically, one is used in the rest of the world, and then the other one is in America. The R value is the American one, and then RSI is the rest of the world. And you can see that the R value, like the resistance to heat flow, right? So think of R as a resistance. The resistance to heat flow is very little in the concrete. That means it's not resisting it a lot. It means it's very easy for it to go. And that's why the U value, which is the transmittance of heat, which means how easily it can transmit heat, is very high, especially the U value of concrete compared to fiberglass, right? There's a huge difference in the number there. And because it's the inverse of the R value or the RSI value, which means it's a resistance to heat flow, there's very little resistance to heat flow. Heat can travel very easily through it. There's not a lot of resistance, but the fiberglass has a lot more resistance, so this number is higher. So, as I was explaining before, you have heat that moves by conduction always, as long as there is a temperature difference between the outside and the inside, right? It's going to go through your walls, your ceilings, your doors, your windows, any place that it can get through, it will. And as long as there's a temperature difference between inside and outside. Now, this is also true in the summertime. It's not just winter. So this is the reason why air conditioners work, like I was explaining to you about the bricks, that if the bricks get really hot, they have a lot of heat stored in them, so they're still giving out heat, even though at nighttime it might be 19 degrees and you have your thermostat set at 22 degrees. So all that heat flow is still going to happen, but if you have a lot of insulation, the goal is that by the time that heat is trying to move in, more heat has escaped to the outside in the summertime than trying to come inside, so that it's lost most of the heat to the outside rather than the inside, so then the air conditioner doesn't need to work more. So that's how heat moves through conduction. So the example of the bricks that I was giving basically is talking about its thermal mass, like how much it's able to slowly heat up or cool down or essentially store heat, right? And how you figure out, so like a material like brick is different than say a material like metal. So even though you might have two things that are the same size, they will hold on to their heat very differently because it depends on its ability to store heat, quote unquote store heat. So you have a part of that is your specific heat, and this is the amount of heat required to change a unit mass of a substance by 1 degree of temperature. And its heat capacity, like how much heat a material can hold, and it's determined by its specific heat and its density, right? And how much thermal storage capacity it has is determined by its density, its specific heat, and how conductive the material is. So we don't need to know too much about this in terms of going through a comparison of materials, but let's at least take a look at some of the materials for their specific heat. So if you're to take cast iron, its specific heat is 554 compared to oak, which is 2400. Alder, so different woods will actually have different specific heat. And here you can compare that to concrete and brick. These are the two examples that I gave. And then water, you can see its specific heat is very, very high. Okay, so let's talk about convection now. And so convection is heat energy that can be carried by a moving liquid or gas, right? So in a liquid or gas, the hotter fluid is also going to be the lighter fluid. and that will rise, while the cooler fluid will also be the heavier fluid, and that will sink, replacing the rising fluid or gas. A chimney is a great example of this. As you heat the air with a fire, for example, that air wants to rise, and then that will establish a strong upward current or draft. So the flue effect is a result of the convection that happens in a chimney or in a flue. Stack effect is a result of convection currents happening in any open area of a building. Convection currents also occur in empty, uninsulated walls. This is also where insulation makes a big difference. It's not just through conduction that you lose electricity in a wall or in a poorly insulated wall. You have heat travels from the warm side through the plaster or drywall by conduction, and then as that air heats up in the cavity next to the wall is heated, it travels up to the top, loses its energy by conduction to the exterior, and then sinks down, and then it starts again. So basically, also the greater the temperature difference, the more you will see this happening. Okay, so here, for example, you have hot air. In this particular case, you can say basically if the hot air is coming from this vent up here, and this attic is actually an insulated attic. Let's assume that for this example. So you have the warm air, and so over here you have the inside drywall and your outside drywall. So let's assume this is winter, and you can see that all this is cold. So if there's any air and there's not a lot of insulation or no insulation in here, this warm air that's coming into the space by conduction is cooling down and coming down, and as it gets colder, because it's losing its heat to the outside over here because it's colder out here, it wants to sink, and as it sinks, it's losing more heat, constantly going down, getting colder, colder, and colder. And this is why sometimes if you're in, like, say, a concrete building or a brick building, and there's not any insulation or not a lot of insulation, you feel cold and drafty. Your feet feel cold, and that's because it is actually colder over here. But the draft, quote unquote, feeling is that air moving as a liquid over here. Right? It feels like it's moving like a liquid even though it's a gas, but you feel that draft across your legs. Now, because of our heating system, you have warm air, and that wants to rise, but as it loses its heat to the wall, and then the wall is actually, it loses its heat by conduction to the wall, and then as this loses heat by conduction to the outside, you have this convection that's happening on the inside losing heat over here and also over here. So materials that are good insulators therefore must have the lightest possible material surrounding the smallest possible air pockets. The light material slows down the rate of heat flow by conduction, right? And then you have the small pockets that constrict the heat flow by convection. So basically you want a whole bunch of small pockets and with the light material. So probably the first examples that you think of are foam. That's why foam can be a good product for insulation, but it has other problems. Obviously, from an environmental standpoint, it is made out of plastic and a petroleum product. So it is not renewable. It is not easily renewable. And especially with spray foam, for example, it is not recyclable. And especially when you're renovating spaces, as people do, those areas that have spray foam stuck to them can't be reused, and you create more landfill. So there's kind of a compromise there on the environmental side of things, but you have other options as well that are great. There are now also companies that build these light structures or light materials with great pockets using bio-based materials to create a better insulation materials. So now let's talk about the third example, radiant heat, right? And so if anybody's been around the fire and the fire is gone, so you're not getting any convection heat from the top, you still are getting convection heat, but most of the heat that you feel when you have these red glowing embers, of these coals, is that radiant heat that is coming out from there, right? And that's what you feel on your hands. And you also have a really big source of radiant heat that I will let you think about as you move on to the next slide. So I'll give you a quick second to think about that. So that tiny source of heat that I was talking about is actually the sun. Actually, it's not tiny at all. It's very huge, and it gives us a lot of radiant heat. And we'll get into that a little bit more. But one thing to understand is that substances exchanging heat do not have to come in physical contact with each other. And that's what we're trying to explain here. They radiate heat in all directions as a function of the absolute surface temperature, right? And this heat transfer is even cooler surfaces are actually radiating heat to warmer surfaces. And what you feel is actually the net energy transfer. So if you have a really warm surface and a surface that's not very warm, they're both actually radiating heat to each other. But because one is really warm, you will feel that the net energy transfer is what you're feeling between the two, and that's what we feel. But understand that everything is radiating heat unless it is at minus 273 degrees Celsius, or in Kelvin it is 0, right? So at 0 Kelvin you don't have any heat energy transmitted by electromagnetic wave motion, and that's how that heat is transferred, unless it is 0 degrees Kelvin. At that point, there's no vibrations happening, so you're not getting any of this radiant heat being transferred. So the best way to explain this is in terms of excited atoms and the nuclei. Electrons in an atom can be ejected from their normal orbits around the atom into those ones further away. And when this happens, the atom is said to be in an excited state. So let's look into that a little bit more. Over here you can see this is a grounded state, where this is a normal space where you have the atoms going around the orbitals with the lowest energy state. And as they get more excited, you have radiation at a specific wavelength that supplies the energy to raise the electrons to the next highest energy state. So when does this happen? This happens when energy that's supplied from outside a substance is converted into thermal motion and then finally into excitation. A short time after excitation, the electrons return to their normal orbits and give off their excess energy, the capital E, in the form of radiation of a particular frequency. So let's take a look and see if we can understand this a little bit deeper. But not a lot. This goes back to the whole E equals mc squared, but this is about the maximum that we're going to get into it. So over here, you can see that these are the electrons, and the electrons that have the arrows moving out are now in an excited state, and they're going from their normal orbit to one that is further out. And as they lose that transmission, they come back to their normal orbit and go into that stasis. So radiation is the energy emitted by solids, liquids, and gases as a result of the absolute temperature. By absolute temperature, we're talking about their temperature based upon the Kelvin scale, because absolute 0 is 0 Kelvin, right? Which is minus 273 Celsius. So this radiant energy is in the form of electromagnetic waves, right? So every time it's losing from the electron is going up and losing that energy and then coming back, and this covers the entire electromagnetic spectrum, extending from the radio wave portion of the spectrum through the infrared, the visible, ultraviolet, X-ray, and the gamma ray portions. So let's actually take a look and see what that looks like. Right? So as humans, all we can see is actually this part, right? The visible. But you actually have a lot more radiation happening all the way from gamma ray to radio, right? Right now, wherever you're sitting, especially in North America, you have all these radio waves that you can use a transistor or a radio to tune into a certain frequency and listen to something, right? So then we can actually take advantage of these radio waves, knowing how they work and tune into those frequencies and take advantage of that energy, right? You have infrared, so infrared saunas, for example, you can't see the heat coming from an infrared sauna, but you feel it. And then you get into microwave, and this is how we cook food, is by exciting the molecules and cooking them. And then on the other side, you have gamma and then X-rays. By exciting the molecules at a certain level, it's able to pass through the body, and then we capture what passes through easily and not so easily. And that's what you actually see in the X-ray, is the picture image of what comes through and what doesn't easily come through the body, because it's able to pass through the body. So most hot bodies on Earth, this energy lies in the infrared range. Infrared radiation is relatively low energy. If it was any higher, we would instantly combust, especially if we could see it. Think about like the colors that you can see when certain things get really, really hot, when normally when they're not hot, you don't see them. I want you to think about a certain thing, or certain objects, for example, where that happens, where in a normal state you don't see them, but if you apply heat to them, they give off this energy even as light and as heat. So think about that for a second, and we'll move on to the next slide while you are considering this. So the temperature of a substance not only determines the quantity of radiation emitted, but also the wavelength. Radiation always travels at the speed of light, so the vibrating speed of the molecule determines the wavelength. The hot surfaces emit radiation at shorter wavelengths, so sunlight is between 0.4 and 4 microns. Cooler, longer wavelengths as they vibrate slower, and you have building surfaces that emit at 8 to 50 microns. And so when I was thinking about that explanation from the previous slide, if you think about a light bulb, for example, that's how it works. You have electricity that's applied that then heats up a traditional light bulb, not an LED light bulb. So I'm talking about the traditional incandescent light bulb. So that's why it's in a vacuum, and you have that seal so that the tungsten filament can superheat up because you're applying electricity to it, and it gets really, really hot, and then it actually changes color so that you're able to see the radiation that it gives off, and that's what you see. And if you were to ever touch those light bulbs, they feel super hot, right? And so that's a part of that as well. So here you can take a look and see how it goes from a warmer surface to a cooler absorbing surface. A way to think about this is maybe this is like you have a cast iron stove, for example, and you've lit a fire in it. It's getting super warm, but you can't see the fire, especially if the stove doesn't have glass at the front, but it's emitting all this heat, right? And so at that particular wavelength, if your leg is near, you are the cooler absorbing surface, so you feel the heat from the stove, and you're absorbing that heat, right? At least initially. And if you get a little too close, then you end up cooking. So that's always not a good idea. So the idea is to understand how this heat moves when these two surfaces are not touching, right? And that's exactly how it works with the sun and the earth. The sun and earth don't touch. If they did, we wouldn't be having this conversation right now. So I'm glad they're not touching. So another great way to think about this is if you're to take a look at a stove, right? And I'm talking about the older style coil stoves, where you turn it on. So say it goes from 0 to 10, where 0 is off and 10 is maximum, and you put it at 2 or 3. So the stove is on, but you don't see any visible glow in it. But if you put your hand over it, you will feel the rays emitting from the plate, right? So or from the coil. So you can't see the heat, but you can feel it. Now, if you crank it up to 10, it starts to glow, and it starts to glow red, and you can see it, and it also feels a lot hotter. And this shows you that the higher temperature of the hot plate, the greater the amount of radiated energy, right? So because of the temperature change and because of the higher input of electricity to make it hotter, you now also have more radiated heat coming out. And that's how you can cook your food faster or burn it very easily. So as the temperature of a substance increases, you actually get more colors on the spectrum, and these are where you have different flames. If you have done any welding of any sort, you know what kind of flame you want for the right kind of weld, and the higher you go, the better the flame. And even if you've gone camping, right, you're trying to heat something up really fast, you're aiming for this kind of blue flame over here. And that's because it's a lot hotter than the yellow part of the flame. And that's what you're trying to get at. So what I want you to think about as we end this is that the sun, wood stoves, and light bulbs, these are all things that we think of as radiating energy. But for us, it's very important to understand that we also radiate heat. I keep saying in this course, I'll continue to say it because it's so important that you understand that not only do we generate vapor, which is why we have to constantly drink water and take in fluids, because we exhale that from our body, not only as perspiration, but also through our lungs and while speaking, as part of our physiology, but we also radiate heat. And that's why we feel cold in certain situations. So it's because we are losing more heat if we're next to a cooler wall or window. So it's not the cold is coming to us, it's that we're giving off more heat. And we notice imbalances, right? That's how we work, and that's how our sensations work. So it's not the cold coming to us, we're just radiating more to the cold surface because of that imbalance. If the temperature outside is closer to our body temperature, we radiate less. And that's how that works. So I hope that was a good explanation, and I look forward to discussing this in class, and have a wonderful rest of your day.